This is a video of examples from chapters 4 and 5 on Newton's laws. So we'll begin with this one of Arlene walking on a high wire, and you need to find the tension in the wire. So the picture that goes with this looks like this. It's not a very big sag, so she's standing here, and the force of gravity on her is what's pulling that rope down. The tension in the rope, if you analyze the point right under her feet, ropes can only pull, so the rope is pulling up to the right, and since it's the same rope, it would have exactly the same tension everywhere, but it would be also pulling up and over to the left. Now, the fact that the two buildings are 10 meters apart has nothing to do with it. What counts is the angle. And it says the angle of sag is 10 degrees. So that would be 10 degrees. Now, if we do a free body diagram for this knot in the rope, well, it's not a knot, it's just where she's standing. It would be this force of tension, this force of tension, and this force of gravity. And they would all have to add to 0. So the x components would be 0 and the y components would be 0. So let's do an x and y coordinates here. There's x, there's y. Now, if it's 10 degrees up there, it would be 10 degrees down here as well. So you would do all the x and y components for ft. That would be ftx. And then you'd have an equal and opposite ftx this way. So you don't really have to worry about ftx. Those two would cancel each other, but you would have two y components for ft, fty and fty. The condition for equilibrium is the sum of the forces equals 0, which means these two components up to fty would have to exactly equal fg, her weight. So to get the y components, you take the sine of the angle, be the sine of 10 degrees, and that would equal mg. So the tension in the cable would be mg divided by 2 sine of 10 degrees. And it says her mass is 50 kilograms. So we have 50 kilograms times 9.8 newtons per kilogram over 2 times the sine of 10 degrees. And that would give us a force of tension in that cable of 1410 newtons. Okay, number 2 is the classic lawnmower problem. And so the way this lawnmower is being pushed is along the handle, and the handle is like this. So this is force applied by the person pushing the lawnmower. And it says that this force applied is 88 newtons. Okay, so what else is acting on this? The force of gravity is acting on this. It's grass, it's pretty rough. Now, it's going to tend to go to the right, so friction would be left. We don't know yet whether that friction, whether this force is enough to get the thing moving or keep it moving or accelerate it. We'll have to do that later. And then, of course, there's the force due to the floor or the grass, the normal force, which is not equal to mg. It's not equal to fg in this case. Okay, so those are all the forces. And now it does say that it is moving at constant speed. That's very important. Moving at constant speed. That tells us the net force must be 0. So this tells us acceleration is 0. Therefore, F net must also be 0, which means all forces balance. So in the x direction, that means that the forces to the right must equal the forces to the left. And in the y direction, all forces up must balance forces down. Okay, but before you can apply the up, down, left, right, you need to get that applied force into its components. Now, the way that it's pointing like that is not a very good way to try to figure out what's going on. It's actually coming out of the center and going this way. And it says it's at 45 degrees. So this is 45 degrees, which means when I do my X, Y, this is 45 degrees. Okay, now it has two components. This would be 88 cos 45, which equals 62.2 newtons. And then this one would be 88 sine 45, which would also be 62.2 newtons. Okay, now I can draw my up, down, left, right. Now that I've got that applied force in terms of its x's and y's. So we've got the applied force component in the x direction, 62.2. We've got friction left. We've got the normal force up. We've got the force of gravity down, and also the component of that applied force down. Now, it tells us the mass of the lawnmower is 14 kilograms, which means we can get FG, which is mg. May as well work that out. So it's 14 times 9.8. And 14 times 9.8, I have to work it out. Is 137. Okay, so this one down here is 137. Okay, now once we have it looking like that, up, down, left, right, and we know up equals down, left equals right, it's real easy to write our equations. So question A, we've done the free body diagram. B was the horizontal friction force on the mower. Well, because we know that right equals left, then we know that the 62.2 newtons to the right must equal the force of friction to the left. Okay, so that's the answer to part B. Part C, the normal force. Okay, so now we know up equals down. Everything's positive. When you use up equals down, everything's positive. So up we have the normal force. That must equal what's down, 137 for gravity plus 62.2. So the normal force must be 199. Okay, and then what force, part D, what force must the person exert on the lawnmower to accelerate it from rest to 1.5 meters per second in 2.5 seconds, assuming the same friction force? Okay, it would be a much trickier question if you didn't know the same friction force. Okay, so part D, first we have to get the acceleration. So the acceleration is VF minus VI over T, because VF is VI plus AT. So we have 15 meters per second. Going from rest is 0, time of 2.5 seconds. So we need an acceleration of 0.6 meters per second squared. Okay, now it says what force must the person apply on the lawnmower? Now we're going to assume it's going at 45 degrees again. But now it's an unknown. So if we go back to here, we have the horizontal force due to the applied force of the lawnmower, which was F cos 45. So that's what is moving it, trying to move it to the right. We've got friction left, which it's said to keep the same. So the force of friction was 62.2 newtons. And so now F net is right minus left. So the net force is the applied force. So this is the applied force along the handle times the cos of 45. That's the component in the x direction. Minus the force of friction, 62.2. So that's our F net. Now we can't calculate that because we don't know the applied force. This is what we're trying to find. This is our unknown. But we know that F net equals MA. And so we know that this is equal to 14 kilograms times that acceleration, 0.6 meters per second squared. And so it has to have an acceleration of 8.6 times 14. So the net force is 8.4 newtons. Okay, so we equate these two expressions. The applied force times cos 45 minus 62.2 must equal 8.4 newtons. And this leads to an applied force along the handle of 99.9 newtons. Okay, so the thing to remember about this question is this, and what students make the most mistakes is this right here. The normal force does not equal the force of gravity. It's bigger because it has to overcome that vertical component of the applied force. Okay, next question. This is the crate when there's friction on an incline. So this is a crate on an incline. And I think I'll do the crate moving to the right on this incline. Now we did one of these when we did our 2D kinematics examples where this is given an initial velocity of 3 meters per second. So someone gives it a big shove, it heads up this incline. Angle of the incline is 25 degrees. But now we have friction. And so the acceleration is not just equal to g sine theta. So now we have to do all the forces on this crate. And then it's going to rise and stop. And we want to know how long this takes. And so it's t up and t to go down. Now these two numbers are not the same when you have friction. Okay, so there is friction here. Now when there's friction, the acceleration is different on the way up and down. So let's do the free body diagram for any mass on any crate. Okay, so this is theta. Our xy goes like this. Force of gravity is vertically down always. That has two components. It has a downslope component. This is theta. This downslope component is Fg sine theta. And the way I remember that is the slippery slope downslope component is the sine. And then it has an inslope component, and that would be Fg cos theta. That's what keeps it from falling off that incline. So, and I remember that as cos close. The cos component keeps the box close to the incline. Okay, now if it's going up, so let's say it's moving up, well then friction would be down. That would be the force of friction. If it were going down, friction would be up. We'll do that in a minute. Now there's also a normal force. And once again, this normal force does not equal the force of gravity. The normal force equals Fg cos theta. So if you just look at the components that count, Fn, perpendicular to the surface always. Inslope component of gravity has cosine. And then the thing trying to pull it down the incline is Fg sine theta and friction. So on an incline, unless someone is pushing at some funny angle, Fn is always equal to Fg sine theta. Sorry, cos theta. Okay, so this is the normal force on an incline. And that is what's going to determine the force of friction. So the force of friction is always mu, whether it's up or down, doesn't matter, is mu Fn. So this is mu mg cos theta. And that equals friction on an incline. Okay, so to get the acceleration, Remember, F net equals m times A. And so A is equal to F net divided by m. This is always true, no matter what's going on. And if we're in the x direction, this is right minus left over m. Okay, so whether it's going up or down doesn't matter. That is how you get the acceleration on an incline. Well, on any object doing anything. Okay, so let's do going up. The acceleration is, there's nothing to the right. It's going up because it's just like a ball that you throw up. It's going up because it has inertia and it's going to carry on going up unless something stops it. And in this case, it's both the component of gravity downslope as well as friction trying to stop it. There's nothing to the right. To the left, we've got the component of gravity, mg sine theta, and we have the force of friction, mu mg cos theta. And then you divide all that by m. So notice how m doesn't even matter. Didn't even have to tell you what the mass was. And so we can get the acceleration, and it's negative because the acceleration is to the left. So it's equal minus g onto sine theta plus mu cos theta. So this is negative 9.8 sine of 25 minus 0.12 cos 25. Okay, so this is the acceleration on the way up. This will be a bigger negative number than when it's coming down. And so the answer is I don't know, I guess I have to work that out. 5 sine, careful, this is a plus. Whew. Okay, so you better check this out, but I get a number of 5.21 meters per second squared. Okay, and this is because it's slowing down on the way up. Not with negative 9.8 because it's not free fall, it's on this incline. So slowing down on way up. Okay, so there's a kinematics question. Remember, we're trying to find time. So time to go up. Well, we've got that VF is VI plus AT. So T is VF minus VI over A. VF is 0. It's given an initial velocity of 3 meters per second up the incline. That's positive because I made up right. 3 meters per second over negative 5.21 meters per second squared. So the time to go up is 3 over 5.21. I would ask for how far it goes. We'll get that in a sec. So how long is this? This is 0.576. That's about right. 3/5.6, yeah, seconds. Okay. The distance up the incline delta x. Now, what's a good one to use? Well, since we know the time, we may as well use that this is equal to 1/2 VI plus VF times t up. This is the distance it goes before it stops. So this is half of 3 plus 0 times 0.576 seconds. And so the distance up the incline would be 0.864 meters. 0.8, half 0.6 is about 3.3, that's about right. Okay, now, what about going down? It has a different acceleration going down because now friction is the opposite direction. Now gravity doesn't change, you still have g sine theta, the force mg sine theta down the incline, but now you've got the force of friction up the incline because it's opposing the motion. And so now the net force, so acceleration, same equation, right minus left over m. But now you've got the force of friction to the right, and you've got mg sine theta left over m. Now the force of friction still has the same magnitude. It's still equal to mu mg cos theta, that's force of friction, minus mg sine theta over m. The acceleration is still negative. It's still going to accelerate down this incline. So it's left. It's going to accelerate to the left. Once again, m cancels, but now we have mu cos theta minus sine theta, all times g for the acceleration. So it's going to be a smaller number. Still negative though. So this is 0.12 cos 25 minus sine 25, all times 9.8. And this will be the acceleration while it's sliding back down. Okay, and this gives a number of negative 3.08 meters per second squared. It's not as big a number because friction's actually trying to hold it up, and so it doesn't accelerate down as quickly. Okay, now it's not at rest by the time it gets back to where it started. So it's now at rest up here. This is the initial velocity is rest. Now it slides down to the point where it started, which we know the distance. Delta x is the 0.864 meters. That would actually be a negative number because it's going left now. But it's moving at some speed, but it's not back to its original speed of 3 because it's lost all this energy due to friction. So VF we don't know, but we don't care. What we want is time. So we've got given here, we've got acceleration as it accelerates down that incline. We know it starts at rest because it had to stop and turn around before it headed back down. And we know how far it goes till it returns to its position. Left, 0.864 meters. And now we're trying to find the time. That's not so simple. So what equation should we use? Well, it's not too bad because VI is 0. So if we use this one, VIT plus 1/2 AT squared. If VI is 0, this is not a quadratic, so this is okay. So delta x is 1/2 AT squared. And so T is the square root of 2 times delta x divided by A. Once again, if you didn't put the negative for that delta x, you would have gotten an error here in your calculator. So this is the negative 0.864 displacement over the negative, what was it, 3.08. And this is T to go down. Okay, so then this would equal 0. So it takes longer, 7.495. So the total time to go up and down, you would add them together. The 0.576 plus the 0.74. Well, that's a lot of sig figs there, 95. If you round those off, 1.33 seconds. Okay, so that's quite a hard question. That's a really good question. The thing you have to remember is it would be like if you throw a ball up and you did worry about air resistance. On this ball, it would be like having a parachute here, slowing this ball down. So that's slowing it down, force of the parachute, force of gravity. It's going to just go whoop and rise really quickly. So it'll rise. But when it's on its way down, it's like having a parachute up. That's what friction's doing, but the gravity pulling down. So now it's going to go la da 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 da. It's going to take longer to go down. So it's longer to go down because it's got less net force in the downward direction. And this is really quick to go up. Quick. Big acceleration. Big negative acceleration, but longer to go down. And that's the same on this incline. It takes quick to go up, so everything's trying to pull it back, friction and gravity, and longer to come down because it's like having a parachute. Takes longer. Okay, so that's a good one. That's number 3. And then the last one here, number 4 is a classic elevator question. You need to know how to do these. Okay, so it's the elevator question. I think I went over this in the summary of these chapters. So I once asked a group of students to actually take a bathroom scale, go downtown, go into a high rise and ride up and down and watch the reading on the scale. Not really expecting them to do it, but some people did do it. And if you've ever been in an elevator that lurches and you kind of feel your stomach rising in your body or dropping in your body, it's because of the acceleration of the elevator. So this is a scale. This is a person. And the forces on the person are the normal force and their force of gravity. The net force on the person is up minus down. And that's equal to m times a. This is always true no matter what the scale is doing. And so the normal force is equal to Fg plus ma, or mg plus ma. And so you can write this as m onto g plus a. That's the normal force. And that is the reading on the scale. Remember that it doesn't read gravity. Gravity never changes. But if you start jumping around on a scale, you can certainly change the reading. And what you're doing by jumping around or riding in an elevator is changing the normal force, the force at which the scale pushes on you, you push equally hard on the scale. So this is a reading on the scale, Fn. Now this is always plus 9.8 newtons per kilogram. That is the strength of gravitational field. That's never negative. But this, it could be 0, or it could be positive, or it could be negative. It depends what's going on. And the mass never changes, whatever the mass is. Okay, so I call this the elevator equation. And you can start right here if you want to for any elevator question. Reading on scale is m onto 9.8 plus a. Okay, so then it says what's going to happen. First of all, it tells us it's a 75 kilogram person. May as well put that in. So it's 75 kilograms times 9.8 plus a. Okay, so part A. It says, what does it read when the elevator is at rest? Well, that would be a equals 0. So Fn would equal 75 times 9.8, and this would be in newtons. Okay, so that would be 735 newtons, or 75 kilograms. Depends how the scale is calibrated, whether it's reading newtons or kilograms. Okay, B, the elevator is climbing at a constant speed. Constant speed is acceleration 0. A equals 0. So it's the same answer as above. Part C, the elevator is descending at constant speed. Ditto. Constant speed, A is 0, same as above. D, the elevator is accelerating up at 3 meters per second squared. So now this is A equals plus 3. So the reading on the scale would be 75 times 9.8 plus 3. And that would be 960. I'm not sure how much that got rounded. Newtons. If you wanted kilograms, you just divide that by 9.8, assuming that's how the scale is calibrated. From newtons to kilograms, you divide by 9.8. And so that would read 98 kilograms. So that would Now this is called an apparent weight. You didn't suddenly just gain 13 or 4 or what, 23 kilograms. That's a pretty heavy duty change there. It's just the apparent weight. That's just what the scale is having to do to accelerate you up at 3 meters per second squared. I don't think there's any elevators around that actually accelerate at that kind of rate. And then if the elevator is accelerating down, that would be acceleration's -3, and now you're going to feel lighter. And so Fn would be 75. The 9.8 always stays positive. Then you subtract the 3. So it'd be 510. I think these have been rounded. Or divide that by 9.8 and you get 52 kilograms. So the reading on the scale varies widely as that elevator is accelerating up and down. Okay, that's it for these questions now.